Attaboy, Mikey. Okay, and I've broken it down into two sets of slides. The first set this morning deals with some of the complexities around measurement and the difficulty that any river presents, right, to the observer in terms of the material that potentially needs to be measured. So we're going to make some general comments there. Then we're going to talk a little bit about the forces involved in getting particles into motion. There's an enormous literature on that. People have spent decades trying to hone in on that. It's a very, very complicated field. So we'll be gentle on the math there, but unfortunately, there's no way around a couple of equations. As always, I'm not going to expect you to manipulate these equations. I want you to understand what terms are in these equations and why they are there. So that's kind of the second component this morning. And then we'll talk a little bit about measurement of sediment in its variety of forms and some of the errors associated with that, right? So that's the first part. And then the second set of slides takes a step back from that and looks at, once we've measured the stuff and we've plotted it, then what do we do with it, right? So why are we going through this whole hassle of trying to figure out what to measure, how frequently to measure it, the errors associated with that, and then producing a particular type of plot that you will produce in the river simulation lab as well, right? And then why we do it, how we use it, ultimately getting to from looking at a small scale section of a stream to predicting continental land to ocean sediment flux using these particular types of plots, right? So this is pretty meaty stuff. I am biased. This is my favorite part of the course. My apologies to statistics and hydrographs and modeling, but I love, even though I've branched out into various other areas in my academic career, I don't know why it is, but nothing gets me more excited than getting into a stream, measuring sediment, plotting the data, and thinking about what it all means. So that's kind of where we're going with the sediment transport stuff. This is one of these slides that I could quite comfortably put into an exam and say, discuss, right? So this is the confluence of two streams, flow moving from top down and from the left to the right, this little confluence of two streams in Costa Rica. What do you notice when you look at this slide? What do you see? What are just some of the, give me a kind of rivers, landscape, geomorphology sort of interpretation as to what you see. Let's get the sediment juices flowing here.
I think in terms of sediment, we're seeing that these two rivers have pretty distinct flows, like as far as like you can see the colors change,
right,
in the different rivers,
right. So there's very, very distinct coloration here in the two streams. Okay. That's often what we look at first within streams. We think of streams as being muddy, turbid, dirty, and others perhaps being clear, right? Sediment, as we'll look at much later on in the course, is a pollutant in and of itself, right? Because when a stream is turbid or cloudy, that impacts photosynthesis, productivity, and so on. Right? So there are two different colors here. Okay, keep going, or someone else, or what else do you? How do we build up a picture of what's going on? Again, did I mention this? This is Costa Rica. I was to say to you, Ryan, do me a favor, just go out and measure the sediment transport in these streams. Tell me what's going on. Nice little challenge.
Oh, well.
Yeah, exactly. Well, where do we start?
I don't know. Would roughness have anything to do with it?
Right. So roughness is a big part of it. Okay, and just look at the variability in the potential roughness elements, right? So we're going out here. This is clearly a sediment grain, quite a large one, right? This would be by definition a boulder, which would move under a certain set of hydraulic conditions. And there's something going on up here, right? It's clearly a deposit, most likely, obviously, made up of fine-grained sediment as well. Right? So there's an enormous spectrum of particle sizes in this diagram. Okay? This one in the top, just incidentally, is draining an area that is part of a national park that really has not had a large land use change component to it, right? It's not all primary forest, but it is largely primary forest. The left one is draining a region that has been deforested. It's going through a reforestation program, but it's also an area that's impacted by cattle grazing coming out of the Guanacaste province, right? So land use, erosion, the production of sediment on slopes that we've talked about, right? Which one has a higher sediment load, which is the total amount of sediment being moved, right? One might argue that it's the bottom left one, it's dirtier, it's muddier, there's more sediment coming out. But in terms of measurement, right, if I just handed you a bunch of equipment, some nets and samplers, and we're going to show you what those samplers look like, okay? You're posed with a terrific challenge here in terms of what do we measure, how do we measure it? Very, very complicated. So that's kind of the premise here, right? We are dealing with an extremely complicated environment as opposed to perhaps an alluvial river that is gentle, that is draining material and delivering material that is all well sorted, medium sand, and you can get a better handle on what's going on, right? So the fluvial environment is complex in and of itself. When you present it as something like this, it makes it even more so when it comes to measuring, quantifying, describing sediment, right? So I just want you to keep that in the back of your mind as we go through this today. All right. So everything should be plugged in. Let's make sure this is working. All right. So just some general comments here on the slides, right? On this image, some themes that we are going to touch on and that we have to keep in mind when we're talking about sediment transport in rivers. One is it's episodic, right? Almost always, because the discharge changes, the flow varies. We know that. If you look at a flow duration curve, we're going to have high events, right? The large magnitude floods that occur relatively infrequently. Then we've got this range of middle flows. We may have low flows. So the flow environment, the regime environment, whether that flow is steady or unsteady, uniform, gradually varied, rapidly varied, the things we've talked about, means that sediment transport is episodic, right? Tremendously episodic. Sometimes there's large amounts of sediment moving. Sometimes there isn't. Sometimes that is a direct reflection of the flow environment. Sometimes it isn't, right? Sometimes you may have a mass movement like a landslide, dumping a huge amount of sediment into or around the river course, and that sediment may be highly mobile and it can get into the channel more easily. So think in terms of the sediment delivery ratio, right? When you look at an image like this, we've got the sediment yield, which is the amount of sediment passing a particular point. So I could put you all, if I could, I'd put you on this cross section here, you'd measure the discharge, you'd measure the sediment, and you'd be able to get an estimate of the sediment yield. Then you have to think about the erosion that's going on upstream of that point, right? Everything that's going on upstream of that point, how much sediment is being delivered. That delivery mechanism in and of itself is episodic. So the entire sediment transport environment is episodic, right? It's hard to quantify. It is, okay? And one of the reasons why it's hard to quantify is that there is always a significant degree of error associated with this, okay? So Dr. Carell talked about a distribution of variables, and you're thinking about means and medians and modes and dispersion and things like that. Even if all of that is easy to measure, when it comes to sediment transport, there's a high degree of error, right? So I could put, again, all of you in this class spaced out across the stream with a sediment sampler, and even if you were not worried about these big coarse particles, if you were just measuring the murky, muddy stuff, right, the stuff that's what we call in suspension, and I'm going to explain all of that, each one of you would come up with a different number, right? Whether that's because maybe Ryan's sitting in a core where the flow is a little faster and moving more sediment there, and Cam is in a quiet pool or something, or if you're both in exactly the same environment, the fact just your measurement technique may be different. So there's a high degree of error, and then there is this notion of how do we measure the coarser and coarser grained particles, right? So this is looking like a pretty bleak lecture, right, from the outset, because of all this complexity that's built into an environment like that. Does that make sense to everybody? Yeah. Okay. All right. I've made a couple of changes to the slides here. I put this up here. I know this looks kind of like a bit self-fulfilling, putting up one's own publication, but I'm doing this for a specific reason, and that is, so I've spent in my early part of my career, I think I've mentioned this before, quite a lot of time looking at thresholds, right? The initiation of sediment transport, the conditions under which that occurs. How can we reduce that error? How can we put sort of confidence bands around sediment transport? This is not my photograph, but this is a friend of mine who's been doing some work on bed load transport, right? And so they're trying to identify the thresholds under which that bed material will be entrained. Okay, so that's a term I suppose we should just put up on the board. So we're going to talk about entrainment. Okay, so entrainment is the initiation and the movement of sediment into the fluid, right? So getting it moving. And those thresholds are very difficult to identify for the reasons that we'll just look at, right? So that's one concept. Remember, we talked about thresholds as a geomorphic fluvial concept at the outset, right? We talked about extrinsic and intrinsic thresholds. These are extrinsic thresholds. These are thresholds that are exerted on the particles by the flow, extrinsically by the flow. So we spend time trying to identify thresholds. But the real complexity, over and above the changes in velocity that may be going on in a channel, comes down to the size distribution of the grains, right? The way in which they're sorted, the way in which they're capped, the fact that their shapes change. This would be a little simpler if every sediment particle in the world's rivers was a perfectly spherical sand grain of, say, 2 millimeters in diameter. Right? Clearly, that's not the case. Okay? We know that the particles range enormously in size distribution, the way in which they're oriented, the way in which they're packed, and so on. Right? So we talk about, and you'll see in the equations, d, which almost always refers to the grain diameter, okay, when we're talking about sediment transport and entrainment and the kind of pick up and go of getting a particle into the flow. So yeah, things would be a little more simplified if all particles were glass beads sitting on a riverbed. When we talk about the grain size, the size distribution of a particular deposit sitting on a stream, okay, when we look at a particle, because they're not perfectly round, they're not spherical grains, we actually, how do we quantify that? Well, a particle has 3 axes. This is just a heads up. So here's a pebble, for example, and this pebble has 3 axes. So there's a long axis here, right, which is A, which is the longest section of the particle. Then it's got an intermediate axis B, which is the width of the particle, and then of course it's a 3-dimensional entity, so we've got a short axis, the height of the grain, right? So if we were to say, what's the average grain size of this particle sitting on the bed? How do we determine that? What do we use? Well, generally speaking, we use the b-axis. We try and find that Goldilocks axis, right? So you would grossly overestimate the grain size of a particular deposit if you were just using A, you would underestimate it if you're using C. And so we use the intermediate axis, and we can estimate the average grain size sitting on a bed. Okay, so how do we do that? Right, so here's how we do it. And this is a very, very simplified and very crude way of trying to tell the flow. Here's what you're looking at. This is the nature of the deposit that you have to work with. So it's known as a Wallman pebble count, after the geomorphologist Gordon Wallman, one of the big names in rivers in the 1960s and 70s, 80s, did a lot of work. And the Wallman pebble count is, we make our students do this when we go to Costa Rica. So here's a view. It's not a very high resolution photograph. I apologize for that. But you're looking down the street here and you'll see probably a red zigzagging line. And so all you do, right, if you wanted to quantify the grain size along a reach of river, okay, I'd make you stand here and you would move down that river from one bank at 45-degree angles, you would walk across that river to the other bank, and then you would get to the bank and go 45 degrees. You would zigzag down the channel, and every step that you take, right, you take one step, you go down, you pick up a pebble. You don't try and sort and say, oh, that's a nice looking pebble. You just reach down, you pick up a pebble, you measure the b-axis. Right? You take another step, you reach down, you pick up a pebble, and you measure the b-axis. Okay, so you do that, and you zigzag down the channel until you have 100 pebbles. Okay, and then you start employing Dr. Carell's lecture from last week. Right, you calculate the mean grain size, you calculate the median grain size to see if it's skewed. Right, is your pebble distribution skewed or not? Do you have a normal distribution of pebbles? It's very, well, I wouldn't say it's very rare. It's rare that you have a normally distributed size of pebbles, especially in a bedload stream like this, right? And there's a whole range of other statistical indices that you can use to describe this deposit, right? So let's just say you're looking at the area in orange here. What's the median grain size there? What's the mean grain size? Okay, does that make sense? Very simple technique on how to quantify the nature of the bed that the flow has to work with. Now, of course, if let's say you came here and you said, all right, the average grain size here, let's say it is 3.2 centimeters. So we're dealing with gravel, right? The average size is gravel. Some are going to be bigger, some are going to be smaller. Okay, and so think about the errors involved of just saying, all right, the flow is going to encounter an average grain size of 3.2 centimeters. All right. Of course, that's just the average. There's going to be much smaller ones that it's not going to take as much energy to move, and it's going to encounter bigger ones that it's going to leave behind. Okay, so that's part of the challenge. All right. So yeah, here we're looking down on the deposit in a stream bed. There's other ways to quantify grain size as opposed to just meandering down a channel and picking up randomly every meter 100 grains. You can have these little sort of cutouts where you can lay it over the stream, and you can say, okay, can I sort of identify what the largest particle is, what the smallest particle is? Really, really crude, right? Pretty crude ways of estimating particle size. Another challenge, I'm just throwing some concepts and challenges at you here. Another challenge is the way in which the particles are packed. Okay, so this is an image from the textbook. So you may have a coarse layer here of fairly loose pebbles and gravel and maybe the odd little boulder. But underneath that, if you scrape that away, you may have much finer sediment, but much more compact. Okay, so trying to quantify the sediment load of that stream, again, will be difficult depending on which of those two deposits the flow is actually engaging with or in training. Or you can try and do something much more expensive and much more sophisticated to try and estimate grain size. So I thought I'd just bring in some of my own work here real quick that we did in Costa Rica. So we're standing in a stream here at our research station in Costa Rica. We're looking upstream, right? So the channel is here, and then it splits. Okay, remember that term, bifurcate. It splits around this sort of vegetated channel bar here. And one arm goes up there, the other arm wraps around the top, and then it joins and keeps going upstream. This is a small watershed. It's about 0.3 square kilometers. So it's a long, narrow. Remember, Dr. Carell was talking about the shape of watersheds. When you've got a watershed that looks like that versus a watershed that looks like that. We're in a watershed that looks like this, long and skinny, very steep, high energy, right? And so how do you quantify the grain size there? Okay, we know that I've seen this during a flood where it's eroding. This is a pretty steep channel bank here, and it's eroding clay soils off the channel bank. But then, of course, it's also got these very large boulders. So how do you quantify the grain size, right? How do you deal with something like roughness? Well, the one thing you can do, okay, is you can bring in a three-dimensional laser scanner. Okay, and we did this back in 2012. It was pretty cool. We had a tripod, a kind of triangular trapezoidal tripod. It's the height of the ceiling. And we took a laser scanner and suspended it off the tripod. And then we moved that tripod meter by meter for 1,200 meters, okay, down this channel and we would do 360 scans. I don't know if any of you have seen one of these scanners. It's like, you know, when you see the chap sitting on the side of the road and they've got a survey rod and they've got a tripod and they're looking through. They're sending out one laser beam. So if I'm trying to see exactly the height that Dr. Carell's glasses are, I would send out one laser beam and it would send it back and tell me to within a millimeter the height of his glasses. Or you can use a laser scanner and send out 6 million scans in about 5 minutes. Okay, and what it produces is something like this. Okay, so this is the data that comes back from something like that. You'll see, so here's the tripod. Can everybody see that? There it is there's the tripod. This is uncorrected, so that's not cleaned up or processed. So you can see the tripod in various places. And it sends out these millions of data points, and what you get back is, this is all still the vegetation. My student cleaned all that up and took all the vegetation out, but you can see as you go up, it gives you a full 360 to about a millimeter resolution. You know, if you've got $125,000 to spend on a scanner and you've got a week to spend in a river, you can get an incredibly high resolution image of that channel that looks something like this, right? So here is the channel. This was the original photograph looking at the bar, right? And that channel meanders its way up. You can really zoom in here. This is part of the section. So I've just blown that up and you can see part of the section. So my point is, you can quantify the roughness in a huge amount of detail, right? If you've got the time and you've got the money and you've got all that. But all of that, so we weren't doing this from a sediment transport perspective. We were just interested in how do you quantify roughness to build into a one-dimensional model, okay? And quite depressingly, after doing all of that, we then did 2 Wallman pedal counts, right? We just thought, well, let's just see how the Wallman pedal count comes out. And the median grain size from the pedal count and the median grain size from the $125,000 scanner came out to within 5% of one another, right? And we're all like, oh, geez. But you get a really good picture of what's going on that you can build into a model, okay? So you can quantify the grain size, you can really do that, but then you're trading, you know, dollars for time, for resolution, and all that kind of thing. Nonetheless, as Dr. Carell would probably attest to, you can put this into a model and say, okay, model, this is a high resolution map of the river, but you're still dealing with the complexity of the interaction of flow and sediment, right? So that's just an FYI. Okay, just some other things before we get going into the actual sediment transport rate. So the movement of a particle, okay, how you actually get a grain sitting on the table here to begin to vibrate and then move into the flow. So we've said that that's called entrainment. Okay, so that's the physical movement of a particle into the flow. It's obviously related to the erosive power of the flow, right? Relative to the nature of the particles that are sitting on the bed surface. And I've just put this in underlined here, that are in a position to be eroded, right? In other words, the particles may be sitting there, but they may not be in a position to be eroded. They may be sitting down here under a deposit, right? Or it may be that situation that I just showed you from Ellen's book, where you've got coarse grains at the surface and lots of fine particles underneath, but the flow can't get at that fine particle, right? Because they're compact or they're hidden, or whatever the case may be. Of course, those particles may not be large sand grains or pieces of gravel or cobble. They may be clay particles, and in which case they've got these electrostatic forces that we call cohesion, right? And I'm going to come back and talk a little bit about cohesion as well. So again, we come back to good old G.K. Gilbert, where this is a force and resistance problem, sediment transport, right? At what point do the forces exerted by the fluid, the flow, begin to equal or exceed the resistance of the particles on the bed, okay? And just another shot to emphasize, I don't want to beat a dead horse here, but just a nice picture here from Canada to emphasize the complexity of this interaction between the flow. Remember, the job of the river is just simply to redistribute excess moisture across the landscape. And then, oh, by the way, it begins to pick up particles and do this geomorphic work, right? And it's an enormously complicated relationship, okay? So my work started in a highly controlled environment in a lab where we could control the rainfall, the runoff, the measurements and everything. And of course, as you scale up and get into the real world, it becomes very, very complicated. Okay. This slide I put in here just to remind myself, to remind you that it's not just where the particles are hidden or not, okay? It's also how they are oriented and packed together. So you may have particles that are arranged like that, or you may have particles that are arranged like that. Okay, the bottom one, if they're tilted over and compacted, that we refer to those as being imbricated. So a flow coming down here in this direction, right, exerting a force on a particle that is perpendicular to the flow is one thing, but the flow coming down here, where part of that force is vectored at an angle, is another thing, right? So the orientation, the grain size, the packing, the cohesion, all of that yuckety mess is all tied up within the nature of the bed. So any questions or comments or thoughts there? Yeah, Ken.
I'm seeing that, like that first picture, the one stream that's really turbid and has like all the sediments throughout.
Yeah.
Do all of these things just not account for those?
So just rephrase it to all, what do you mean to all these?
Like all these methods, because I know those sediments are obviously really, really tiny.
Yeah.
But I feel like it would influence the mean particle size that's being transported. Do we just kind of ignore them?
No, great question. No, we don't ignore them. We can, right? But so you don't ignore them in terms of the measurement. Let me see if I don't want to make sure I answer this. So if you're in the turbid one, measuring the stuff that's in suspension, the very fine grained one, is a whole set of constraints, and we're going to talk about that and how you calculate and measure that. And how do you measure the stuff that's close to the bed? How do you measure the stuff that's large and rolling along the bed? You can't ignore it, right? It all has to be built up into this picture of the nature of the bed that the flow interacts with. But we do partition out material that's being transported in suspension and material that's being rolled and sliding along the bed. Does that sort of, okay? Yeah. You can ignore it, but you do so at your peril. Okay, so yeah. All right. Here's another bit of depressing news. Right, let's keep the news depressing for a bit in terms of sediment transport. So this is an interesting plot. It's a little dated, but it's an important one because what this shows is the results of a range of lab and field experiments, right? Looking at the flow conditions under which particles move, okay? And on the y-axis here is bed shear stress. Okay, so let's just remind ourselves of shear stress. Tau equals the density of water times the acceleration due to gravity, okay, times the depth of the flow times the slope. And if you remember that, we saw that a few times. We combine these two terms into the specific weight of the water, so that's a constant. That's good, right? So we've got the depth of the flow. Remember, well, there's a depth, there's a hydraulic radius. Let's just think depths to simplify. And the slope. So we've got shear stress on the y-axis as measured really carefully in the lab and in the field, okay? And we've got grain size on the bottom axis in millimeters. So here we're just looking at coarse materials, sands, you know, even beyond sand, right? 10 millimeters, that's 1 centimeter. Sand is 2 millimeters and above. So this is all gravels and pebbles and cobbles and larger granules, right? So I should make that point. So this doesn't include the suspended messy stuff. And this diagram is partitioned out. This is all the dots and X's are from a variety of studies. And the bottom line here is that anything that is a little black square is where the scientist was observing movement. The particles were moving under that particular set of flow conditions, right? And X is no movement, right? So the shear stresses that were measured indicated no movement of particles, okay? And so what do you notice here, right? So there's a region here where there was no motion, right? And the region in the top left where there was motion relative to particle size. And then you've got this kind of messy transitional area in between, right? Where we have some studies were showing movement and some studies were showing no movement, right? This diagram for me summarizes the complexity of sediment transport for all the reasons that we've just touched on. Flow variability, grain size variability, cohesion, packing, orientation, yada, yada. Does that make sense? Right? So you would have one study where the grain size is 10 centimeters, okay? And you've got a shear stress of 10 newtons per square meter, right? So if you've got a shear stress of 10 newtons per square meter, in other words, you've got pretty shallow, pretty slow moving flow, there was no movement observed, okay? And then you come up here at 100, okay, at that 100 millimeters or 10, then you've got potential movement. There are some studies that show no movement and some studies that show movement. But up at 1,000 here, that 10 millimeter particle absolutely would move all the time. Does that make sense, what you're looking at here? And the take home here is that this is, 2 orders of magnitude, right? This is a 10-fold difference in the measured shear stress. This is a 100-fold difference. In other words, the range where you could potentially see movement or potentially not see any movement is huge, right? 2 orders of magnitude in this particular diagram because of all the complexity. So you may be asking yourself, well, why don't we just shut it down here and go home and drink coffee and not worry about any more sediment transport? Well, we can't. Okay, let me stop there. All good, makes sense. Everybody happy with that? That is a really interesting paper, pretty dated. And since 1983, I don't know, Gehendra, if you know of anything, but we haven't really made a huge amount of progress, right? Beyond really trying to identify those thresholds. Now that doesn't mean to say that this is a hopeless task. Doesn't mean to say that we should not measure suspended sediment or bedload sediment to begin to calculate big things like sediment yields and sediment delivery and so on. So we'll also examine that, right? That issue of scale. All right, we're doing on time. We're good. I love this stuff. Okay, so that's a little bit about the complexities, the errors, the constraints that a particular river imposes on a flow. Okay, let's talk about what we call the get up and go. Right. So let's get nitty gritty here and start looking at sediment transport. The forces acting on an individual grain. Right now, I know. Okay, well, what is it? Is it a big grain, a small grain? So we're going to start simply. Here's our grain. Okay, kind of looks like an apple, but we are going to use a nice round little spherical grain sitting on a bed. Okay, and as I've said, any particle will move if the force that is exerted on that grain is greater than the forces of inertia, the forces that want to keep that grain sitting there, right? So that's the starting point. And these here are vertical velocity profiles within a channel. So the velocity is 0 at the bed and it increases. Okay, and it's just showing reversal of flow. So flow is coming out of the right and reversal of flow on the left. So the forces are being exerted on this side of the particle. It's just a fun little graphic just to emphasize that the forces are being exerted on that particular grain. All right, cool. It's neat. I like it. Okay. And this one here with these translucent particles, this is a photograph that someone has taken. It's quite a well-known photograph from, I think, a study in the 90s, looking at the velocity as you move away from the surface. Remember our friend roughness, okay? And as you get above the particle here, the roughness decreases pretty quickly. So the flow lines are, it's not a laminar flow per se, but they're more or less parallel. Things get a little messy around this particle because of the turbulence and the interaction of the grain with the flow. Okay. Okay. Now, the caveat here is I'm not going to expect you to derive any equation in an exam, but I really want you to understand what's going into these 2 equations on either side of the particle, the force and the resistance. So there are forces that want to move a particle, okay, and those forces are lift and drag. And there are forces that want to keep that particle in place, okay, and those are the acceleration due to gravity and any other kind of force that we lump under resistance, including, very importantly, cohesion, right? These electrostatic forces between particles, especially clays. So we've got a particle, and this is a nice little diagram showing the X and Z here. So we're looking at 1, 2, 3 centimeters. So this is a 3 centimeter by sort of 2 to 3 centimeter particle. The white area is a more or less spherical grade. And this shows the measured velocity fields above that particular grade, right? So the velocities here are 85 to 90 centimeters per second. And then the velocity field gets dramatically distorted as it begins to interact with the grade, right? Because of friction. Okay. So in looking at the sediment transport equations, we are just going to deal with gravity and drag, right? Those are the two major forces, okay? It's not that lift is unimportant, right? So how does lift occur? Remember, this is how airplanes fly, right? So if we've got a wing, let's draw a wing in side view there. How does an airplane fly? Well, those four forces all come into play, right? Okay, so there's drag and lift. The drag is the acceleration, and there's the gravity and the inertia that wants to keep the plane there. So when you've got airflow coming into contact with the wing, an aerofoil like that, right? How does a plane get up? Lift. That's the primary force that is created to get the plane vertical. And how is that lift created? It's created by the distortion of the airflow over the wing, where this is increased velocity here, and the air slows down here. So this is decreased velocity. Okay, and as the velocity increases as the flow lines increase over the airfoil here, the velocity increases, that decreases the pressure. And as the air slows down underneath here, it increases the pressure, right? So higher pressure here, lower pressure here, and there is a force between high to low pressure. That's the lift force that's created, right? That makes sense. And as you orient the airfoil on a plane to increase the speed over here, the aerodynamics, that increases the lift force. Right? It always blows my mind that a plane can be flying at 120 miles an hour or 150 miles an hour and still be suspended in the air because of the lift force that is created underneath that aerofoil. So the same principles, of course, hold true for a particle, right? Sitting on the bed. Okay? So here's this particle, this little white bubble here. Okay, and here is the fluid velocity. So we've got high velocities above the particle, much lower velocities here. Okay. So that creates a lift force, right? So the pressure is higher here and lower here, which creates a lift force to try and get that particle into the flow, right? But in the big scheme of things, the lift that is created by the change in velocity is not nearly as important as the drag that is exerted on that particle, right? By the flow itself. So we're going to ignore lift and we're going to ignore cohesion. We're just going to look at gravity for the moment. Does that make sense? So we're going to look at this balance between the forces of inertia that want to keep the particle there and the forces that want to move that particle by the fluid. All right, here we go. So we'll keep it simple, right? And again, all we're doing here is predicting this entrainment, this get up and go. So there's our grade, our beautifully spherical grade. And we've got these two forces, the forces that are hindering movement, right? The resisting forces due to inertia, that's primarily gravity. And we've got the forces that want to get that particle going, the fluid drag. Everybody with me? All good? Okay, sweet. Again, lift we're just going to ignore for a moment. And we just can't deal with cohesion at the moment. So let's just deal with a nice sand grain sitting there. We're not going to worry about that ugly thing to cohesion. Okay, so the force of resistance, right? The resisting forces, the forces that want to keep that particle there, is simply the mass of the particle times the acceleration due to gravity, right? The weight of the particle. What is the mass of the particle and the acceleration due to gravity? Now, fortunately, this is a constant, right? The acceleration due to gravity. So it comes down to what is the mass of the particle, right? Obviously, if you've got a particle that is sitting on a bed that is made up of polystyrene, it's going to be very different to a particle sitting on the bed made up of lead, right? So the mass is important, okay? And so we can replace, and so mass is ugly to deal with, and so let's replace the math. Again, don't panic if you kind of like, wait a minute, here's some math, don't panic, right? We can replace this mass term, right? So in color, we can't ignore gravity. So gravity is there. But we can replace the mass term here, this air, okay, by just talking about the volume of the particle, right, and its density. Okay, that's easier to deal with computationally. It is. So we replace the m with this, right? So the volume of the particle is 4/3 pi r cubed. Right? That's how you calculate the volume of a sphere, of a sphere, right? Multiplied by the density of the particle. Well, you do have to take away the density of the fluid, okay? Because the fluid is giving that particle some sort of buoyancy. So let's take the fluid out. So we take the density of the grain. How dense is that particle? Is it polystyrene? Is it quartz sand? Or is it a lead? You know, is it a blob of lead? So we take the density of the grain minus the density of the fluid, get the fluid density out of there. And if you multiply that, the density of the grain multiplied by the density of the fluid, and you multiply that by the volume of the particle, then you're off to the races, right? That gives you the force of inertia multiplied by the acceleration due to gravity, right? I mean, I guess that comes down to the bigger, the wider, the heavier, that's the greater the force of inertia. But that's the equation. Everybody good? No panic yet. Awesome. Okay. Well, we can do a little bit of algebra and combine this into a constant. So Z is just a constant here, right? So we can combine the constants into a single term, and what it comes down to is that the force, the resisting force, is d cubed, right? So the diameter of the particle cubed, multiplied by its density, multiplied by the acceleration due to gravity. Right? That is the resisting force in the calculations of sediment transport, which is really nice and easy. We can calculate what the diameter of the grain is quite quickly. Okay, well, yeah, some are going to have a long axis or short axis, but in this case, we're dealing with a ball, right? So the tennis ball is sitting on the bed. We just measure the diameter, cube it, multiplied by the density of the grain minus the density of the fluid. The constant is empirically derived. Everybody with me? That's the force of inertia in a sediment transport equation. Okay? That is the force that wants to keep that particle there. What is the acceleration due to gravity? How big is the particle? And how dense is the particle? Happy on the home front. Graham, Caleb, all good. Awesome. No questions.
Good.
Sweet. All right. So that's the resisting force. Okay. Now let's talk about the force being exerted by the fluid, right? So this is the moving force. Okay, and the most important variable here, and you probably would have been able to argue this from first principles coming in here, is the velocity, right? Now, don't ask me why in sediment transport equations, maybe Dr. Carell can explain it to me, but we don't use V to illustrate velocity, we always use U. I don't know why. I don't know what the history of that, probably Chow 1964 or something, would be my guess, right? So the moving force, the fluid force, right? The force being exerted on the particle, right? So this is that fluid drag. Just think of it, I want to push this particle over and get it moving, okay? Is, and I have decided to skip the derivation here. So we've got a constant, so that's cool. So the force that will move the particle is what is the area over which that force is being exerted on the particle. So it's the diameter of the particle squared. Okay, we're not worried about the volume here in the density. We want the diameter. So how much of that particle is exposed? If I'm in the water and there's a basketball sitting right on Ryan's head, what is the diameter of that particle squared, right? Multiplied by the density of the fluid. Okay, because now this is we're concerned with the fluid and the velocity, and U is the velocity, and it's U squared, all right? Because velocity does this in a river, right? It goes up non-linearly. So that's the force that's being exerted on the particle on Ryan's head. How big is it? What's its diameter? Okay, and what is the velocity that's being forced up against that square? Beautiful, right? And so the initiation of movement is just simply that balance between the inertia and the fluid drag, right? The F subscript R, the force that wants to keep that particle in place. So that's the diameter cubed multiplied by the density of the particle multiplied by the acceleration of gravity relative to the fluid drag, all right? The velocity squared that's being forced onto that area of the particle that's exposed. The density of the fluid is important. The nice thing about this is that we just take this as 1, right? 1 gram per cubic centimeter, because the density of water varies just a little bit. This equation would be different if we're trying to measure particle sediment transport in onto minus zero, okay, or something that has a much higher viscosity or density. Does that make sense, everybody? So we're just looking at the balance, right? Force and resistance. Here's force, there's resistance. When the forces exerted on the particle begin to approach the resistance, then you're beginning to move towards this quote-unquote threshold at which the particle will begin to move and begin to probably vibrate and then finally go boink, and off it goes into that flow. Okay, right? And the nice thing about this is that we can combine both of these terms and do some magical jiggery-pokery, i.e. math, right? And we can solve for the velocity. And this is what it looks like. Okay? Don't be scared of this equation, right? But this is the one that you'll see in all the textbooks, right? That for typical river conditions, U, and now it's got that little asterisk, and we call that U star. That is the shear velocity. Okay, that's a really, really important term in fluid mechanics. It's the velocity that you need to reach for shearing to occur. In other words, for that particle to, I'm resisting, I can't resist anymore, right? For it to quote unquote shear off a particular bit. So the U star, the critical shear velocity, if we just, and I'll go back a second, all we're doing is we're combining these two, the force and resistance. The shear velocity equals 0.06, don't worry about that, that's a constant, empirically derived. Square root of density of the grain minus the density of the fluid, so it's still the density of the particle, multiplied by the acceleration due to gravity, multiplied by the diameter, right? And that is the most elegant and simple expression of sediment transport, that there is a critical shearing velocity, which is really a function of the diameter, the acceleration due to gravity, the density of the grain, the square root of that multiplied by an empirically derived constant, right? That describes this shear velocity, and this is the important part of the bottom, it describes the maximum particle size that can be moved under a given velocity, right? In other words, if you had a particular velocity, you could predict what is the maximum particle size that should move, okay? For ideal river conditions, typical river conditions, and you're just probably thinking, now hang on a second, didn't you just show us that diagram with movement, no movement, and 2 orders of magnitude? Yeah, forget about that, right? That's a much more complicated sense, because now we're looking at a whole range of particle sizes. This is for a particular particle size. And we can do that, and that's called the competence of a river. So when we talk about river competence, the competence is the velocity particle size relationship. What is the maximum particle size that could potentially be moved under a given velocity? Does that make sense? Right? Okay, and it's shown by this diagram. This is a very, very famous diagram. There was a typo in the book here. That's not meters per second, that's centimeters per second, just FYI. So if you're looking at this in the book, there is a typo there. But this is a really, really famous diagram. You can see this was 1935. This is pre-World War II by a scientist called Hillstrom, who was doing sediment transport experiments. What's not known is this was actually done by his grad students. David, he took all the credit. This was my diagram, but it's a very important diagram that shows the relationship between velocity and particle size. Okay, and you can see 3 domains here, right? There's an area of deposition, an area of transport, and then an area of erosion. And this gray curve, right, is the erosion velocity. Now remember, you saw something similar to this a while back. Particle size, remember kinetic energy of rainfall to detach 1 kilogram, yeah, and it looked like something like that. Ooh, that looks awfully familiar, right? And we had this envelope, right, that looked like something like that, okay? So here it is again, but this isn't for raindrop detachment, this is for fluid, all right, where your errors are a little lower relative to the variability of rain. So this is the erosion velocity, and this is the deposition velocity, and you've got these 3 domains, right? So how do you work your way around this diagram? Well, let's say we're dealing with a sand grain that has a diameter of 1 millimeter, right? Here's a sand grain of 1 millimeter, medium sand sitting on the bed, okay? In order to get that sand grain entrained, in other words, moving, you have to have a velocity here of somewhere between 10 to 30 centimeters per second. That will erode it and move it. Does that make sense? Okay, to get it off the bed and into the flow. You can drop the velocity a little bit here to keep that sand grain transported, but if you reach this velocity here, which is about whatever it is, 8 centimeters per second, sand grain goes and falls out into deposition. Make sense? Right? Or you look at another sand grain here of 0.1 millimeters. Okay, so this is an order of magnitude smaller, right? So here you need about a 10 to 11 centimeters per second to get it going, right? You still need a similar velocity to get it going, but you start dropping that velocity and it can transport. Now you've got to get it down to about 1 centimeters per second, and then it'll eventually fall out, right? Make sense? So any particle in a river should plot somewhere on this diagram, all right? So the gray curve is the erosion curve, and the dashed line is the deposition curve. And you can see the challenge of cohesion, right? Okay.
So the deposition curve is keeping it in place, holding it down.
The
And then the erosion is what's kind of straight and flip off the top.
So the erosion curve, the erosion curve is the velocity to get the particle entrained, and the deposition curve is the velocity you have to reach for that particle to fall out and deposit on the ground, right? Does that make sense? So this is why this curve is like your supervisor, right, Dr. Holbrook. This is why he would use this to explain why you get such variability in grain size in deposits and sedimentary structures. It's the fluctuating variability of the velocities, right, that will entrain and keep things. In other words, to get clay entrained, you need a very high shear velocity. Because of cohesion, the electrostatic forces, those clays are packed together and they have cohesive properties. So you need a high velocity, right, to get a clay moving. But once that clay is eroded and you drop the velocity just a little bit, it stays in suspension for hours and hours and hours. It won't fall out, right? So if you've ever done a soils course or a sediment size, and you have a graduated cylinder and you put clay in there and you suspend it, it's going to stay there for at least 8 hours over a 10 centimeter distance before it finally goes, okay, I'm tired, I'm going to settle that, right? You don't have to change the velocity much at all to keep that clay happy and suspended. Does that make sense? But this line, as soon as you start getting into the silts and the sands, you have to, look at this, you need 100 centimeters per second to get a piece of gravel transported, but you drop that velocity a little bit and the thing just falls out, right? So I'll show that here as an example, right? So here we're looking at, if we just take a particular velocity, so let's say at 5 centimeters per second, anything in these grain sizes is in transport, this will be falling out and deposited, okay? So if your river's moving at 5 centimeters per second, nothing's being eroded. We're not even up at the erosion line. We're either in transport or deposits. Fine material in suspension, muddy river in Costa Rica from the left, or clear river in the top of the diagram, things have fallen out. Now we go through a flood, right? Dr. Carell's now plotting his hydrograph and separating runoff and surface and all of that cool stuff. We raise the velocity here. Let's say we raise it to 80 centimeters per second. So we increase the velocity by an order of magnitude. Now we are eroding stuff. We are eroding silts, we're eroding all of this fine stuff and probably getting gravel to move on that riverbed and getting it into entrainment, right? The flood wave goes down, the hydrograph disappears, maybe the velocity goes back to 0.8 centimeters per second, right? Now, most of the core stuff is fallen out and we've probably just got some silts and clay in transport. Everybody make sense? So we're kind of looking at the force and resistance, but just in terms of erosion, transport, and depositional environments. All right. Thoughts, comments, questions? All good. A lot of stuff coming at you. All right. So that's sediment transport. Let's keep going just for a little bit here. Let's talk about sediment load, right? So how is sediment transported in a channel? So there are 3 types of load, right? The amount of sediment that's being transported in a channel. There's flotation, dissolve, and then there is the true sediment load, right? Three big broad types of load. This photograph always takes me back. It was one of the most memorable days, and to be honest, this is the picture that kind of got me. I think I'm going to study sediment transport for the rest of my life. We were in the Namib Desert in Namibia. I should have put a map up here. It's a desert that floods once every 3 or 4 years, or this river, and this river separates sand dunes from gravelly desert. And we decided, we were up on a field trip there. This was as an undergrad, and we decided to have a barbecue in the river, and then we heard some rumbling. And we were there just as this river flooded, and it was absolutely extraordinary. And we saw all different types of sediment transport, but let's just look at these individually. I'm not going to spend much time at all on flotation and dissolve, other than to mention it, and then we'll get to the sediment load, right? So flotation is anything that's floating on the top. You'll see this in the river simulator, okay? So this is vegetation, right? So this is anything, leaves, sometimes this is quantified under the acronym LWD, big chunks of vegetation, or what we call large woody debris. And this can be hugely important in terms of river morphology and the dynamics of a flow. So this is not my picture, it's taken by a friend of mine who teaches at the University of Oregon, right? So flotation load deals with vegetation and how that interacts with the flow environment, okay? So yeah, this is the picture of the tripod in Costa Rica. Flotation load is important here, right? Lots of vegetation on the forest floor and vegetation that you can see scattered throughout here. So it's part of the load, right? And vegetation can also be very important in terms of storing sediment. I mean, we know how important beaver dams are, right? In terms of regulating flow within a channel. But we get a lot of these kind of log jams, as to what these are called, where vegetation and then sediment begins to build up behind the flotation load. So, you know, it's a bit naughty of me to completely ignore flotation load, but we're going to, because we just don't have time to spend on flotation load. So flotation load is one type of load in a channel. Dissolved load is another, okay? So this is we talk about TDS, the total dissolved solids. And this is important in terms of the world's load, and especially important in karst, right, where water is infiltrating into limestone and dissolving that material, and that material gets transported out of the region in terms of dissolved load. So it's important, but again, people who are into karst are going to turn over in their graves that we've just spent 45 seconds on dissolved load. But this is where we're going to spend our time, right? It's the sediment load. So not flotation and not dissolved. So this little diagram here, I think does quite a nice job of explaining this. We tend to think of the sediment load in terms of suspended load and bed load, right? Material in suspension, so the muddy, dirty river in Costa Rica, and then the bed load, the material that is being pushed along the bed, the coarse grades. It is a little more complicated than that, and this, I think, is the preferred terminology, right? Is there is a suspended load and a bed material load, right? So there is material in suspension, and there's material that is from the bed itself, right? The grain sizes mimic what is sitting on the bed. So there's bed material and there's suspended load, right? That suspended load is made up predominantly of what we call wash load, fine grain material coming to the river from surface runoff and the erosion of the channel banks, right? So we're talking about fine sands, silts, and clays here, the stuff truly in suspension, right? The wash load. But the suspended load can also be made up of material sitting on the bed that is temporarily in suspension. If the flow is fast enough, you can get coarse-grained particles temporarily suspended, right, by the fluid, the turbulence in the fluid. So suspended load is made up of predominantly wash load and some temporarily suspended bed load, okay? But the bed material load is always either true bed load, large material rolling along the bed, or some of that material that gets off the bed and is temporarily suspended. So that, I hope that didn't hurt or confuse, but that's a graphical view of what I always think about as being sediment load, right? again, most people think just talk in terms of suspended load and bed load, and that's okay. But this takes it one step forward to saying, one step further, to say that suspended load is predominantly fine material, but also temporarily suspended stuff from the bed. All right, so let's just look at this graphically. So wash load tends to be silts, clays, very fine sands, right? You get material that where you get channel bank collapse. So here's a bank that is collapsing here, and the fine grain material will be entrained by the flow. Okay. We tend to think of wash load as supply limited, right? In other words, that's a really important term. In other words, the velocities, the shear velocities, the discharges tend to be high enough to transport the wash load, because we're just talking about clays, silts, and fine sands. The limiting factor is how much of that material is being made available to the channel, right? In terms of the production on slopes and the delivery to the channel itself. Okay? And it's generally a pretty well mixed load by the turbulence. So here's an example, right? So here's the channel down at the bottom here. This happens to be in Australia. So there's a channel over here. Here's an agricultural field. And here's concentrated flow coming down these rills. That's delivering fine grained silts, clays, and fine sands to the channel, right? Some of it's getting deposited in a fan here, but ultimately some of that may make it into the channel and end up being the wash load, the suspended load, supply limited, right? If you cut off the erosion here, then the channel only has the bed and the banks to work with in terms of its supply, okay? Versus the bed material load, right? Which tends to be not supply limited, but what we call transport limited. In other words, when you look at this, so this is the Brazos River. I took this picture a few years ago in the Brazos. Pretty low flow, lots of material there to be transported, right? We've got bed load here, we've got all of this stuff sitting in a sandbar, but we don't have the flow conditions to actually transport that, right? So that is not supply limited, it is transport limited. Okay. There can be some of this material that is temporarily suspended, as we just talked about. And the bed material load, the grain size distribution of material that's transported by the bed material load sort of mimics the stream bed particles. So this is a simplified diagram just to sort of illustrate this, and then we'll begin to wrap this up, right? So the bed load, right? So this is bed load here, and this is suspended load. Material in the bed load can be transported by rolling. So this is true bed load that is not getting into the flow at any particular time. Those particles can be pushed along, they can slide along. You can have impact where a particle is rolled and bumps another one, and that other one begins to move. So this is all lumped under what we call traction transport. Okay, coarse material that is pushed along the bed of the river, of the bed load. But remember, some of that bed load can temporarily move into suspension. Okay, temporarily move into suspension. And when it does, we often talk about saltation. Okay, saltation. And saltation is a really important mechanism of sediment transport in wind, but also in river. And saltation is where a coarse particle moves into the flow, comes back down to the surface, impacts the surface, and ejects other particles into the flow. So it's bouncing along, right? So it's sort of lifted up by the turbulence, and then it impacts the surface. And that saltation can be uninterrupted. In other words, you can have a particle, you get a pulse of velocity, it lifts a coarse particle up, and then it puts it back down on the bed, right? Or it can be interrupted where it gets into the flow, there's a little turbulence, it keeps it, and then it puts it back, right? The bottom line of this is that all of this is occurring close to the bed versus something above it, right? Which is suspension. And suspended load is generally what we call continuous suspension, because remember, once you get those fine particles into the flow, you have to drop the velocity substantially for it to fall out. And because flow tends to be turbulent, right? The Reynolds numbers tend to be higher, the Froude numbers tend to be higher, in at least in a flood. Most of that occurs by continuous suspension. There is this thing called intermittent suspension, which is particles that are suspended and the grains are bumping into one another. But I tend to just lump these two together, that there is material in suspension, kept in suspension by the fluid, and then material along the bed. Does that make sense, everybody? Okay, cool. All right. Let's stop there, because I want the measurement's going to take about 20 minutes or so, maybe a bit longer. So let's put a halt to that, and we'll come back and address this, and that is how you measure and where you measure determines what you capture, which may seem self-explanatory more. All right, any questions, gang, on the beauty and the majesty of sediment transport and shear velocity versus the forces of inertia? Okay, so next time, which is quite a time from now, right? Yeah. So I'll do a quick recap, and then we'll get into sediment rating curves. That, I think, will set you up for what we're going to do in the river simulator. Good. Have a great spring, whatever it's called. Be safe. See.